only 3 minutes late. Okay, Haley.
Haley. Okay, 1.3b.
Okay.
I probably should look at the questions. But I know it was proving that you can't find a solution.
Yeah.
Yeah. And this, okay, obviously I looked at the answers, but the compatibility, whatever, is that just something that we're supposed to know, or?
Well, okay.
Because I couldn't find it in the notes.
Okay. So, well, I'll talk about this problem in generalities, parts A and B both, and that'd be a good idea anyway.
Okay.
All right. Because this doesn't really conform to anything that's laid out in the chapter exactly, but I'm going to do some simple examples soon. But this problem's kind of weird. So to solve a PDE that has this form, like for example, du dx is some function, I'll call it g, of x and y. And u is a function of two variables in this case. So it's a function of x and y. So what you can always do, if it's this simple a form where you just have this one derivative to deal with, you just integrate both sides. So in this case, you would integrate with respect to x. But then you have to be careful about what you do next. What?
So if you prove that, like, those two integrals can't be equal?
That's
Okay, cool.
yeah. So what you get is on the left side you just get u, your solution, and that is equal to some antiderivative with respect to x in this case, because you integrate with respect to x. Now here's where you have to be careful, especially for those of you who haven't gotten around this problem yet. What do you normally do when you do an indefinite integral? What do you have to remember to add on to it?
Plus c.
Yeah, but this is a function of two variables.
So it's the y.
So what you add on is not a constant, it just has to be something that is independent of x.
Which it would be.
So I'll call it h of y. And this is, at this point, undetermined. It could be, well, based on what we have here, there's nothing else specified, this could be any function of y whatsoever, because when you differentiate with respect to x, it's going to go away. And you just have a derivative of this, which is little g. And that's the antiderivative of little g. So in this problem, in part A, you have two of these equations. One where you integrate with respect to x, the other integrate with respect to y. So you integrate both ways, and you match them up, and find out if there's a way to make them match up with the initial condition that you were also given. So in part A, it's possible to make them match up. In part B, it's not. You have two function forms that are just incompatible with one another. So that's what that problem is about.
So if they don't match, what happens? Like,
There's no solution.
there's no solution.
Yeah.
If they match, that is the solution.
Yeah. So ill-posed problem.
So, like, you would integrate the first one with respect to x and the second one with respect to y?
Yeah.
Okay, yeah.
Okay.
Okay, 1.5b. I forgot what my question was.
Okay.
Okay, B and C, okay, I get that you can't find the solutions, or an explicit solution, right?
Right. Yeah.
But, hold on, let me try to remember my question, I'm sorry. Oh, okay, in B, is there some, okay, since you're letting P of u equal u, or whatever, can you, like, does that, like, I guess imply that, like, the f of x plus u times t equals just the argument, like, x plus u times t? Does that, like, imply that, or do you have to, like, let that be a statement or something?
Well,
That's the only reason you can find the...
okay.
No.
So the thing is, in this problem. Okay. So.
And they move you off that
I have to be very careful here. I have to keep an eye on this thing because I lost about 2 minutes, but at least what I had on the board is preserved. So hopefully that. Well, last time it only happened once. Hopefully, it won't happen again. So as long as I am constantly checking this and seeing when it pops that up and quickly stop and restart, then it should be okay. Okay, so at the point where it cut off, we were talking about the implicit solution. Yeah. So what I was saying that didn't get caught was we have like u is equal to f of x plus ut. You can pick an x and t, plug those in, and then solve for u using an iterative method or like a numerical method like Newton's method. So in a real application, but that's not a concern for this problem.
Okay.
Okay, were there any other questions?
No.
Okay, good. So that's gonna be real nerve-wracking. Have to keep an eye on this stuff. Okay, now let's see where are my proper notes. Okay. Now, I'm going to go through. I have to go through the notes in a somewhat out of order fashion because there are certain things I definitely want to make sure I cover today, and as for the rest, it's not as important. So if that happens, if I don't get it all, that's still a big deal. Okay. So I'm going to go through sections 1.5 and 1.6 that are quite short, and then loop back around to 1.4, which is a very long and painful section, and actually not all that essential. Okay. Okay. Now, so a well-posed problem that, among other things, must have a unique solution. So what we're really solving is not just a PDE by itself. You can have an IVP, an initial value problem, which includes a PDE, like ones you've been solving in the homework, along with an IC, and I'll be using these abbreviations all the time, so it's important to get used to them now. An IC is an initial condition, or it could be more than one initial condition. So that habit starts at initial time, it was time dependent. And this is for an unbounded spatial domain. So for instance, if you're solving a problem on the entire real number line, x goes from minus infinity to infinity. So no bounds at all. So like even a semi-infinite one, like x greater than 0, would not fall under this. Okay, so that's an initial value problem. Or more generally, or most of the time we'll be looking at IBVP, an initial boundary value problem, where you have some bound on your spatial domain. So an IBVP consists of a PDE plus one or more initial conditions plus one or more boundary conditions. Okay. So I want to spend a little time talking about those these side conditions, either initial or boundary conditions, that these problems will feature that we're looking at all semester long. So there are different types of these conditions that you can have. Okay. All right, so first kind I want to talk about are initial conditions. So for example, if you have, and I'll use an example to give some context here. So suppose our PDE is du dt is equal to, let's say, some constant alpha squared times uxx. So this is just the heat equation. Okay. So an initial condition would be u of x 0. So it's understood that your spatial variables generally go first. And then if you have a time variable, that is listed afterwards. So it's understood here that you have any value of x, if a t is specified to be 0, is some given function f of x. So this is kind of like in your first differential equations course, like 285. You had a given ODE, and then you had some initial condition given that when it was first order. Another example that will come up quite often, if you have a second order time derivative. So utt is c squared uxx. This is the wave equation. Because it's a second order time derivative, you're going to have two initial conditions. So u of x 0 is f of x, and then the time derivative at t equals 0 is some other given function g of x. So whatever your order of time derivative you have in your PDE is the number of initial conditions that are required. Okay. Now this is something else that rarely comes up, but it does happen. And sometimes what you can have is an end condition. So an example of that would be, for instance, du dt is equal to, let's say, minus alpha squared uxx. So this is the backwards heat equation. And instead of specifying at the time t equals 0 and then evolving forward in time, because that's the ill-posed problem, you may have your end condition. If you're solving this on the time interval t between 0 and capital T. So instead of specifying the solution at time 0, you specify at time capital T. U of x capital T is equal to f of x. And then you're solving the heat equation backward in time from that end condition. That is actually a well-posed problem, because you can do a change of variable, like change t to minus t, and then you're going forward in time again. All right, so these are the kind of conditions that we can have related to time. Okay, at least my 461 lecture is uploaded. Okay. Now, talk about boundary conditions. Now, stick with my example of the heat equation, where we can also talk about not just mathematically what the boundary conditions are, but also what they I mean physically. So suppose we're solving the heat equation. This would apply, the same discussion would apply to many other PDEs on a finite interval. So we'll stick with one-dimensional case, but there are multi-dimensional analogs to this. Okay, so this is my PDE. Here's my initial condition, like before. Okay, so my boundary conditions, my BCs, here are three commonly used types. The first type of boundary conditions are called Dirichlet. Dirichlet boundary conditions, you specify the solution on the boundary. So in this problem, what that means is you're saying that so your boundaries are x equals 0 and x equal L. So right over here. Okay. So G1 and G2 would be given functions of t. In many problems, you have homogeneous boundary conditions, so the boundary functions are equal to 0, and those are a whole lot nicer to solve. Okay. So whenever you hear Dirichlet, it means it's the values of a solution on the boundary that are specified. Okay. The second type are Neumann boundary conditions. Not Newman, Neumann. And in that case, what you do is you specify, instead of a solution itself, you specify the normal derivative. In other words, the rate of change as you are exiting the domain. Now, in this case, this is one dimension. The only way you can travel is along the x direction, so it's just du dx. Okay, so the normal derivative on that boundary is specified, so you're going to have du dx at x equals 0 equals some given function, and then du dx at L equals x equals L is equal to some given function. Okay. Right. So, and also those are going to be 0. So for a heat equation, U is equal to the temperature. So if you have Dirichlet boundary conditions, what on earth is that? Oh, okay. So for Dirichlet boundary conditions, you're stipulating that the temperature is equal to a certain value on the boundary. Whereas with Neumann, you're specifying the rate of change with respect to x at the boundary. So if you have du dx is equal to 0 on the boundary, what you're saying is that that your domain is insulated, because you're saying that you're not allowing the temperature to change at those endpoints. Because if you're modeling heat equation in one dimension, it's like you're modeling the temperature of like a thin rod. So you're saying the rod is insulated at the endpoints. All right.
You sub x equals 0 means like the temperature remains unchanged across the interval, or
Right. Well, at that point. Yeah.
at the boundary points.
Yes.
So it may have changed, in between, but the net change is 0.
The thing is that the 2 points don't interact.
Right.
So at this one point, there's no change. Like you're having a horizontal tangent. And at the other point, also a horizontal tangent. So the temperature levels at the two may be much different, but
the rate of change is 0.
right.
Right.
At those points. Yeah. Okay. All right. Now the third type of boundary condition, these are called Robin boundary conditions. They're also called mixed boundary conditions. So this is where you have a linear combination of the Dirichlet and Neumann cases. So you may have like alpha 1 u of 0t plus beta 1 du dx of 0t equals some given function. And then similar at the other boundary. So the combination of u of lt and du dx at lt equals some other given function. So these don't come up quite as often, but they're common enough that they're certainly worth mentioning. And they have a physical meaning in this case. So when you have so this is used to specify the temperature of the surrounding medium. And there's more detail about this in the notes, but basically what you're doing is you're stating that, so this is due to Fourier's law of cooling. So this matches the flux, which is the normal derivative, so du dx, against the well, there's actually two laws of cooling here. There's Newton's law of cooling that works at the temperature of the surrounding medium, and then there's Fourier's law of cooling that equates this outward flux of heat energy to the normal derivative. So what you're doing is you're taking what Newton's law of cooling gives you, which states that the flux of heat energy is proportional to the difference between the temperature of your object and the temperature of the surrounding medium. And Fourier's law of cooling says that this outward flux is proportional to the normal derivative, so du dx in this case. So if you take these and equate them to each other, so you take the formula for Newton's law of cooling, set equal to the formula for Fourier's law of cooling, that actually gives you a boundary condition. So for instance, what is happening, I'll draw this, for instance, from a case of this one-dimensional heat flow. And that'll make it easier to see. So here is our rod that corresponds to the interval x equals 0 to L. Okay. Now, Newton's law of cooling states that the outward flux is proportional to, so there's a proportionality constant H, is the temperature at x equals 0 minus the temperature of a surrounding medium, which is a given function g1 of t. Fourier's law of cooling says that the same quantity, the outward flux, is proportional, so there's another constant proportionality k, to the inward normal derivative. But if you're going into the rod at x equals 0, that is in the positive x direction. So the inward normal derivative is just going to be du dx. So what you do is you just set these two equal to each other. And that is your Robin boundary condition. Now, so sure enough, so boundary condition turns out to be HU of 0t plus, or I should say, minus k du dx of 0t equals hg1 of t. So that is your Robin boundary condition for x equals 0. Now, for x equals L, so the upper boundary, it's a similar idea. You have, you're equating two expressions for the outward flux. But there's going to be one slight difference in what you set up here, because Fourier's law of cooling says the outward flux is proportional to the inward normal derivative. So you're going in this direction. So how's that going to change what I write here, aside from the fact that instead of plugging in x equals 0, I'm going to have x equals L. But otherwise, what's going to be different?
Will they change like the U of 0 t and the
Well,
Like-
anywhere you have where x equals 0, I'll have x equals L. But there's something else that's going to be different.
like the G2 of t will change?
Well, that'll change, but one other thing. Inward normal derivative.
It will be negative.
What will be negative?
Negative du dx.
Yes. So we'll have HU of LT plus K du dx of LT equals Hg2 of T, just because an inward normal derivative at the upper boundary is going into the rod the opposite of the x direction, so it's minus du dx.
So G1 and G2 are just given functions.
Yes. Okay. All right, so this gives you an idea of boundary conditions that we have and what they might mean physically. So for instance, if you're given a initial boundary value problem, but it's described more in words, like for instance for heat flow, you're saying at the boundaries of endpoints of a rod are insulated, that just means du dx equals 0 on the boundary. So, so actually these are some problems that were given in the other PDE class, 417, 517, where the problem specified in words you translate into the appropriate initial and boundary conditions. Okay, so questions about that? Okay. All right, so now, okay, how we're doing on time here? Oh, pretty good. All right, so that's all I have for section 1.5. So now we're going to take a look at some simple examples of PDE. So this might actually be helpful somewhat with the homework and how you go about solving these. Okay. Well, first, I'm going to look at what appears to be the same PDE, but first in one dimension. So we have just a function of one variable, so really it's an ODE. U double prime is equal to 0. So I'm not going to specify anything else like initial conditions or anything like that. We'll just look for a general solution here. So what would be an obvious way to come up with U in this case? Yeah, go ahead and integrate. This indefinite integrals with x. So what does that give us?
Well, it should give you a constant.
Yeah, so u prime is equal to a constant, and I'll call it c1. Now, the thing is, when you have indefinite integrals on both sides, it's tempting to put plus c's in both cases, but because they're arbitrary constants, you really only need to put it in one. If it's an indefinite integral on both sides of the equation. Okay, and then,
Like c1 of x plus c2.
yeah, so you can integrate the second time, and you get c1x plus c2, and that is the general solution. And so if you're given initial conditions, then you would use those. In this case, you would have to have two initial conditions, and you can use those to determine the values of c1 and c2. Okay, but now let's change this to 2D. So u is a function of x and y. And you still have the same PDE, but now I really have to write it as a PDE. Uxx is equal to 0. So, can anyone tell me how the fact that I'm going from 1D to 2D, how this would play out differently?
Wouldn't be a constant.
Because you have a function
Function of y.
Of y, yeah. So you integrate once, and you get u prime of x is, call it
c1.
c of y, and then you integrate again, and you still have c of y times x plus another function of y. So now, whatever initial conditions you're given, those would be functions of y instead of just constants. All right, so you can still go ahead and integrate in simple cases like this. You have to be careful about what you add on. Okay. Questions about this one? All right. Let's look at another. This one's a little stranger because you can't just, well, there's a couple different ways to do this. Okay. In fact,
I have a question.
yeah.
Why is that C of Y instead of C of X?
Oh, this is playing the role of a plus C, so it has to be something that's independent of
Okay.
X. Yeah.
Never mind, that's
Okay.
better.
All right. Now, actually, this is not what I have in my notes, or what the equation is, but the approach I want to try here is not what I have in my notes. What would be a logical, if we want to try the same thing, integrating, what would it make sense to integrate with respect to?
This
Yeah, this one.
X
Yeah, because each term
has an
involves derivative with respect to x. So, well, what would that give us? So, okay, well, first I'll write down what we're doing. So, integrate with respect to x. And what would it give us?
that's the partial.
UY plus U equals
I mean a
C
constant.
of Y?
Yeah, because we integrate with respect to x. So whatever we put over here has to be independent of x. Okay, so this is some function c of y. So now what we have is, well, it looks like an ODE, except you keep in mind that u is still a function of two
Now you
variables.
integrate with respect to Y? No?
Well, the trouble is that you can have just
That-
integral with respect to y. So, here's what you could do instead. You could use an integrating factor here. So if I multiply both sides by e to the minus y, actually just e to the y.
Product rule.
Yes. Okay. Then what we have here is e to the y u with respect to y is equal to this. Okay. and then what?
You can take the e to the y outside, right?
Not yet.
Okay.
What should we do now? Because the idea is this is a product rule in reverse, so this is derivative of this whole thing with respect to y.
Now you integrate this.
Now you integrate with respect to y, so you get e to the y u is equal to the integral of e to the y c of y dy. And this is still written as an integral, so we don't have to change anything yet. But so now this would, but once we carry out this integration, actually, this actually works out pretty nicely because, well, not nicely as we'd like it to, but because everything here does not depend on x at all. Okay, now this over here is a function of both x and y. But what's going to happen is once you integrate this with respect to y, you actually need over here something that depends on x.
Would you have
Well, an additional term. So I'm going to call it like d of x equals that. So now I can say that u, if I isolate u, is going to be e to the minus y minus d of x, going to move that to the other side, plus e to the minus y integral of e to the y c of y dy. Now, as it turns out, this is reasonably consistent with the formal solution kind of I know, although it's a whole lot more complicated. So this technically works, but I'm going to show you another way that you might find more to your liking. Just because, even though it's consistent, because c and d are arbitrary functions of y and x respectively. But what I'm going to show you instead, it's also in my notes, is cleaner. And it's useful in a number of situations for solving equations like this, where you try to reduce any sort of differential equation to a simpler one. Okay. So an alternative approach is to solve the original equation, uxy plus ux equals 0. But then d equal du dx. So then if you substitute that into here, you get vy plus v is equals 0. So now you can go ahead and solve that. And using the approach that I described earlier, except with being 0 on the right-hand side, that simplifies things. So you can say dv dy is equal to minus v, so that means that v is equal to e to, we can treat this like a separable equation. Actually, I'll go ahead and do that a little more explicitly. Well, let's see. Actually, treating it like a separable equation, that doesn't really work so well in multivariable, but that's okay. You can do the integrating factor thing. So now you have e to the y v is equal to some function of x. So now you have v is e to the minus y times some arbitrary function of x, which is similar to what we had before. But now you can, the v is equal to du dx. So now you can integrate again with respect to x this time. So u is equal to the integral of v dx, which is e to the minus y antiderivative of d plus some arbitrary function of y, because you're integrating with respect to x. And since c and d are arbitrary functions of their respective variables, you can see how this solution is consistent with the other one, but like I said, this is cleaner. So, questions almost done here.
Whoops.
All right, let's see. Oh, still a good amount of time. All right. Now I have one more example in this section. Okay. Don't want to be switching boards too often. So this is an inhomogeneous wave equation. So we have utt minus 4uxx is equal to sine t plus x to the 2000. That doesn't look contrived at all. Now, solving this as written would be kind of a pain, but there's a way to break this up into two problems that are much easier to solve. So I let u be equal to v plus w, where, because this PDE is linear, so it's easy to break up into a sum like this. So I can say vtt minus 4 vxx is equal to sine t, and then wtt minus 4 wxx is equal to the other term, x to the 2000. And what I can do is, since the right-hand side only depends on t in this case and x in this case, is I can stipulate that v is just a function of t, and w is just a function of x. Because what that means is, like with v being a function of t, that means that vxx is 0. So this term is going to be gone. And since w is a function of only x, wtt is 0. So that term is gone. So now we have two, basically, ODEs to solve. So a lot of times you can decompose PDEs into ODEs in various ways, and we're going to see other ways as we go. That's really all it's about, is just trying to reduce these to the simplest equations possible. So if VTT is equal to sine t, then how are we going to get V?
Integrating.
Yeah, just integrate twice. So what are we going to get?
Negative cosine and sine. Negative sine, right?
Yeah, minus sine. Okay. And then what about W?
Well, integrated twice. So x to the 2000 by 4 integrated twice is.
Yeah, so divide by minus 4,
Okay,
and we'll have, yeah, so when you integrate a power of x, what happens to the exponent?
increase.
Yeah, and we're going to integrate twice, so we have x to the 2002. So we're going to have 4 times
2001 times.
2001 times 2002. Yeah. So what about your calculator?
Someone got creative with that.
So, okay. So, okay. Now, so you can add those together and get your solution. So u is equal to v plus w. But in fact, there's something else you can add on, because I can actually add on, and this will become clear when we learn more about the wave equation. I can add on any function of this form, f of x minus 2t, or any function of x plus 2t.
The phase shift?
You're having shifts to the left or right. And the speed, that is the square root of this coefficient right here. Because if I look at the function like this, f of x minus 2t. So I differentiate with respect to x. So that's going to be f prime of, okay, I'm being kind of abusive of my notation here, but deal with it. That's just going to be f prime. fxx is going to be f double prime. But now, if I look at derivative with respect to t, so that's f prime, but then, I differentiate the inside with respect to t, so I have a factor of minus 2, and then I do it again, and I get f double prime and another factor of minus 2, so I get a 4. So what that means is ftt minus 4fxx is equal to 0. So it satisfies a homogeneous version. So this brings up something that would have come up in an ODE class. Here we have an inhomogeneous PDE. We have a non-zero right-hand side. You can add to it any solution of the homogeneous equation, because it's a linear equation. These are two general solutions of the homogeneous wave equation. So you can just add on any such function and still the solution satisfied. What's interesting is the book only mentioned this one, but that one works just as well. So, go figure. Okay. So what would happen in ODEs, where you can find a homogeneous solution and you add on a particular solution, say this general solution of a homogeneous equation, that same thing works with PDEs. That part is no different. Okay. All right. Now, during the rest of the time, I want to mention some PDEs of interest from applications. Some of these we actually won't get to deal with during the remainder of the semester because they're later in the book. Like, I think we only go up to chapter 8, and some of these appear in chapter 10. But they're still worth mentioning because of the applications involved. I held off to this because this section is not really involved with homework. It's just really interesting because it describes real world relevance. Okay. Now I mentioned before the heat equation. I want to say a little bit about how it's derived. Because what you have is conservation of energy. So physical laws like this are where PDEs come from. So I'll write out the equation and I'll explain what the individual parts mean. This is the 1D case, although same thing applies in higher dimensions. Okay. So we have a rod. That we're modeling heat flow in. Here we have a segment of a rod starting at a certain point x, going to x plus delta x. The cross-sectional area of a rod is this value a here. U, oh, that's du dx over here, sorry. U is the temperature at any point on the rod at any x and any time t. Okay. All right, let's see. C is a term you probably haven't heard since K through 12 science class, specific heat. Rho is density. Oh, yeah, I tried to avoid chemistry in college.
So, A is the cross-section area of that part, right?
Of any part of a rod. We're assuming it's constant.
Oh, okay.
All right. Now, so what we can do is, I can actually use the fundamental theorem of calculus in reverse. Because you can think of this as being like big F of B minus big F of A is the integral from A to B of big F prime of x dx. So, so doing it here, this is the same as the integral from x to x plus delta x of the derivative of this, which is uxx of s and t. Yes, I have to use a different letter here because I can't use x because that's a limit of integration. So now what I can do is I have integrals with the same limits on both sides. So I can combine these into one integral on one side, set equal to 0. So I have C rho, actually I have A's on both sides. I'm just going to cancel them. So C rho du dt minus K uxx ds is equal to 0. But the thing is, I chose an arbitrary segment of the rod. This whole thing holds on any segment I choose. So the only way that the integral over an arbitrary segment of this function can be 0 is if a function is 0 all the time. So this must equal 0. So out pops the PDE. du dt is equal to k over c rho uxx. So that is the simplest form of a heat equation for one-dimensional flow. Okay. All right.
That's the what equation for it?
Sorry, what?
What did you say?
For heat flow. It's a heat flow in a rod. But now this is one dimension. In n dimensions, it's du dt is some constant which I'll call alpha squared Laplacian of u. So that's how it generalizes to higher dimensions. So uxx plus uyy in the 2D case, for example.
But then the coefficients may not be like, you know, the continuous or not.
Well, they might vary. Yeah, here we're assuming that these things are constant.
Okay.
So in fact, if it were not constant, we'd have the divergence of the coefficient times the gradient. And so that's how it works in a multi-dimensional case. And that's because of the Gauss divergence theorem. Let's use it to derive it in higher dimensions. Okay. Now, okay, still have some time left. Now, in the notes, I take time to derive an equation in higher dimensions, and it's extraordinarily ugly. And time consuming. So I won't repeat it here. If you want, you can take a look at how it's all done out in the notes, which I thought was a little clearer than what was done in the text.
What's the n minus d?
Oh, ND, n dimensions.
Oh.
It's not subtraction. It's a dash. Okay. So other PD of interest. So Euler's name pops up again. Euler fluid flow equations. I'll explain the notation in a little bit. Rho t plus the convergence of rho u is 0. U dt plus u gradient of u equals careful. This is a Greek letter rho. This is a ordinary
P.
ordinary letter p. Okay. Now rho. Okay, so this is from the problem we're solving here. Okay, so we're dealing with fluid. Rho is density. P is pressure. U is a vector field, that is velocity. So it incorporates the speed and direction of travel. In fact, we have three variables, so we need a third equation. We assume that the pressure is some known function of the density, just to make everything unique. So what's happening here is, this is kind of strange, U dot gradient symbol. So this is actually equal to U1 ddx plus U2 ddy plus U3 ddz. And all of that is applied to the vector field U. Now the thing is, everything in this second equation here, this is a vector equation, so it actually has three components. Okay. All right. Now, this fluid flow model neglects friction between molecules of a fluid. But if you incorporate that, right, so then you get some different equations. All right, so we get rho ut plus, it looks much like the second equation. But a different right-hand side. So mu is a coefficient, that's viscosity of the fluid, which is needed to account for the friction between the molecules of a fluid. Okay, Laplacian of u minus the gradient of the pressure again. And the divergence of the velocity field is 0, which means that the fluid is incompressible. Divergence of a vector field indicates the tendency of a vector field to move away from a certain point. So if there's no tendency to move away from a certain point, then we say the fluid is incompressible. So these equations are very important. These are called the Navier-Stokes equations. These are ones that if you can prove that they're well posed, then you win $1 million.
Both of those are called that.
Yeah, the system, yeah.
For 3D, right? I mean,
Yes,
like,
yeah.
laminar flow is pretty much.
Yeah,
And
yeah.
then it's like for 3D, you know, then the turbulence pops up, and yeah.
Yeah.
I tried to read up on that and understand it.
Okay. Now another variation of the Euler equation. So we go back to these. So Euler equations lead to a lot of other equations. So you neglect gravity. And you assume that the fluid is at rest. So that means, for instance, the velocity is 0. The density is constant. The pressure is constant. Okay. So you have all of these things, but then you perturb the gas locally. In other words, you, for instance, send a sound wave propagating to it. So the fluid is acting like a medium now, and you have some wave propagating through it and disturbing the fluid locally. Then you take a Taylor expansion, and what you end up with after a lot of manipulations that are in the notes is an equation like this: rho tt minus f prime of rho naught, Laplacian of rho is 0. And a similar equation holds for the pressure. So pressure Tt minus something times the Laplacian of P is 0. So this is a wave equation. Where f prime indicates the speed at which waves can propagate through this fluid. Yeah. Now we'll derive, the wave equation can be derived in a whole other way, and actually I do that in the notes for a vibrating string, so wave propagation in one dimension.
In the wave equation, are those all rows? Or is that last one P?
All of these are rho.
Okay.
But yeah, you do have a similar equation for P. I'll try to make them more distinguishable. Ptt minus this plain Laplacian of P is 0. So the two equations are
What is this now?
both a wave equation. So you can look at it from the point of view of either variable. Okay.
You're saying f prime is the speed of propagation
Uh,
of
Yes.
the fluid?
within the waves through the fluid, yeah.
Is that just delta P1 equals 0?
Uh,
It's supposed to be a 1?
oh, that's-
Oh, okay.
Okay. All right, so this same PDE comes up if you're modeling a vibrating string, as in the one-dimensional case. That's it's called a telegraph equation in that case, but it's synonymous with a wave equation. So I've done that in the notes, and that just comes out of Newton's second law. So all these well-known physical laws that you've heard of in other classes can be used to derive PDEs. You're just assigning functions to all these various quantities that you're modeling, and then stating the given law of conservation of whatever as mathematically. I mean, you do some manipulations that you'd likely learned in multivariable calculus, and out comes your PDE. So it's generally how the process works. Okay. This equation is called the transport equation. So if you have some substance that is traveling through a fluid, so a transport equation describes the concentration of that substance at any point in time or and location within the fluid, so you can model how it's progressing.
You do like stuff in blood?
What?
Like stuff in blood?
Yeah.
Plasma or whatever?
Yeah, or for instance, contaminants in the water.
Okay.
So you can model what's going on in Flint, for instance.
Blood. We'll go with blood.
Okay, that's fine. Okay.
It just cracks me up how like that's what he goes with versus what he goes with.
No, because
They're
that
the
makes
same.
more sense, like one has like plasma or like, nutrients or, I don't know, like all those items.
Well, that's what makes sense. But
And then we get a long
Okay.
order when like they throw a body in the river and they track it back together to the end.
Wow, Candace.
Anyhow, okay. Shoot, I'm almost out of time. Okay. Ooh, jeez. Is that even right? Oh, no, the slide's taking my notes, but no biggie. Okay, I'll just do this one more, and then we'll stop. Okay, so geometrical optics. This is one of these equations we're going to study later on, in the next chapter. So we have wave equation again in 3D. And notice I put 3 t's by mistake. It should only be 2. I was typing too fast. Okay, so this is wave equation. So we assume that u is a function of, so x is a vector now in 3-dimensional space, is e to the I omega t. So this describes a time evolution times some function of only x. So if you go ahead and substitute this into here, then that's annoying. What PE does psi satisfy? It satisfies this one, a time-independent problem. Okay. Now this is an important equation in its own right. This is called the Helmholtz equation. This is very important in seismology, for instance.
What?
Seismology, modeling earthquakes.
Yes, of course.
Yeah. Okay. N is the index of refraction. K is called the wave number. So you can think of it as a frequency. And we're assuming that K is large in this case. So usually the wavelength is smaller than any other length scale you have in the problem. So now we make an assumption about psi. Assume that psi is equal to e to the I k s of x, a of x, where k is a parameter. And you substitute this into this equation, and what you get is, this is fudging a bit, I'll admit, that the gradient of this function s is approximately the index of refraction. And this is a vector magnitude. So this is the Euclidean length of a gradient. So ds dx squared plus ds dy squared plus ds dz squared take a square root. This is called is a nonlinear equation. This is really interesting because these equations are linear, but a nonlinear equation pops out. This is called the Eikonel equation. Okay. So that's something we'll study some point in chapter 2. Okay. So a lot of times, certain PDEs are solved by, if you know something about the form of the solution, you can substitute that in and perhaps some simple equation pops out. Now this is not as simple as we'd like because it's nonlinear, but there are very fast numerical methods for solving this one. Okay, that's all the time we have. But we also covered everything from chapter 1 that could be relevant from homework. Of course, you have still a fair amount of time for homework, so we can take questions on those in class on Wednesday if need be. Okay, so, well, I guess for some of you, enjoy analysis.
Yeah, right.